In this video, we look at Slater determinants. They are used to construct antisymmetric multi-electron wave functions that satisfy the Pauli principle. The Pauli principle requires that physically valid many electron wave functions must change sign when two electron coordinates are interchanged. Formally, the exchange operator pKl operating on a multi-electron wave function psi 1, 2, and so on k, and so on L, and so on all the way up to N, exchanges electrons number k and number L, and is required to give the negative of the original one. This is the Pauli principle. There's a general and simple systematic procedure for constructing correct antisymmetric many-electron wave functions from one-electron wave functions. This procedure makes use of Slater determinants. They work as follows. Take an electron configuration, say 1s alpha, 1s beta, which is simply 1s squared. Next, write down a matrix of the associated one-electron wave functions. In row 1, use the coordinates for electron 1. So 1s alpha 1, 1s beta 1. In row 2, use the coordinates for electron 2. So 1s alpha 2, 1s beta 2. Here, 1s alpha 1 is a shorthand for psi 1s of coordinate 1 times alpha of coordinate 1, and so on. On a side note, remember that a one-electron spatial wave function, such as psi 1s, is called an orbital, and it's only the spatial part. Whereas a function like psi 1s alpha is called a spin orbital. It's a one-electron wave function with both the spatial and the spin coordinate. For the Slater determinant here, we are using spin orbitals. Now, take the determinant of this matrix, indicated by vertical bars, and pre-multiply it with 1 over square root of 2. This is the normalization factor. If you expand this determinant, we get 1 over square root of 2 times 1s alpha 1, 1s beta 2, this is the product of the diagonal terms, minus 1s beta 1, 1s alpha 2. This is the product of the antidiagonal terms. Now, let's determine how this wave function behaves under exchange of the electrons 1 and 2. P12 operating on psi 1, 2 equals 1 over square root of 2 times 1s alpha 2, 1s beta 1, minus 1s beta 2, 1s alpha 1. The first term here is just the negative of the original second term, and the second term after the exchange is equal to negative of the first term. Therefore, this is overall just the negative of the original function. It is antisymmetric with respect to exchange, as it is required for a physical many-electron wave function. Writing this in terms of a determinant, we get 1 over square root of 2 times the determinant of 1s alpha 2, 1s beta 2, 1s alpha 1, 1s beta 1. We see that exchanging electrons 1 and 2 means swapping the first and the second row. Determinants have the useful property that swapping any two rows or any two columns changes the sign of the determinant. So again, we see that we get negative of the original function. Therefore, determinants automatically satisfy the antisymmetry requirement of the Pauli principle. What does the sum of products actually mean in a wave function? The first term says that electron 1 is spin up and electron 2 is spin down. The second term means that electron 1 is spin down and electron 2 is spin up. Together, they indicate that it's impossible to tell which electron is spin up and which is down. This is due to the indistinguishability of the two electrons. Let's write down the Slater determinant for a general wave function for n electrons. Uppercase psi of 1, 2, and so on all the way up to n equals to 1 over the square root of n factorial, this is the normalization constant, times the determinant of psi 1 of 1, psi 2 of 1, all the way up to psi n of 1 in the first row. In the second row we have psi 1 of 2, psi 2 of 2, all the way up to psi n of 2, and so on, row by row, with the different electrons until you get to psi 1 of n, the nth electron, psi 2 of n, and finally psi n of n. The columns contain the different spin orbitals, and the rows contain the different electron coordinates. This wave function is automatically antisymmetric, since exchanging 2 electron coordinates amounts to exchanging 2 rows, and for determinant this results always in an overall sign change. Again, the prefactor here is a normalization constant that makes sure that the overall wave function is normalized. This is a general expression for a Slater determinant. In summary, Slater determinants are a simple and systematic way of constructing antisymmetric many-electron wave functions from products of one-electron wave functions. They work by writing down the spin orbitals as columns and the coordinates as rows in a determinant, and pre-multiplying by a normalization factor of 1 over square root of n factorial.